Hello students, Miss Lim here. Have you ever had a jar? Like a jar, hopefully with something inside, not empty like mine. And you just, well, they're really hard to open sometimes, and you're like, some people say to use like a knife or something, but man. So we could probably say that Miss Lim is putting a fair amount of energy into opening this jar, but she's really slow. And if I wanted to sketch this out, I could think of like, I've got a jar with a lid, and I'm not an artist, so I apologize, right? And I'm trying to open the jar, so I'm trying to get lid separated from the jar. Right? That's my basic process I'm trying to do. And we could say that right now, Miss Lim is spending a lot of energy, and her speed in opening the jar, well, she's gonna starve because she can't open it fast enough. So what do you do with this? Fortunately, weak Miss Lim has a solution. My trusty rubber band, right? Put the rubber band around the lid. Some of you guys might have your own special dishcloth or something. And suddenly, rubber band on lid, so much faster, so much less energy expended. Now what's happening? So with the rubber band, I'm realizing that my little reaction I'm trying to do here, my little separation of the lid from the jar, has a very different effect in terms of energy. In fact, I might even say that the energy that I'm expending is a lot less. And the speed, well, I was way quicker with my speed. Bands are magical, right? They make my energy go down so that I can speed up my reaction. And this rubber band is representing what an enzyme does. And today we're going to talk all about enzymes. Now, enzymes belong to the biomolecule category of proteins. They are made of a string of amino acids, all bound together to form a polypeptide, a bit like beads on a chain. However, proteins are quite complex. They fold on themselves multiple times, forming new chemical bonds, and then finally you kind of end up with a clump. So for today, when I represent my enzyme, it's going to look like a clump. Let's take a look at this graph here for a second. Which line represents the reaction or a chemical reaction with an enzyme? If you said the bottom one, congratulations, you can read. And then the top line is going to be our reaction pathway without an enzyme. What do you guys notice reading that y-axis? What do we have less of when we have the enzyme? Yeah, I would say that I have less energy expelled when I am doing a reaction with an enzyme. And that energy is going to be something I call activation energy, the amount of energy I have to put into a reaction in order to kickstart it. Think of activation energy once again with our jar and a rubber band. I have to put a little bit of energy into this, just a little bit, in order to actually separate the two molecules, to have the reaction go through. And that extra energy, the energy I put in at the beginning, that is your activation energy for a chemical reaction. Let's start capturing some of this on page 9 of our notebooks. Did you bring your notebook to class today? I'm looking at you. So I'm going to title page 9 Enzymes. I'm going to draw a line down the middle. Well, not quite down the middle, but you get the idea. Okay. My first term is going to be, an enzyme is going to be a protein molecule that speeds up chemical reactions by lowering the activation energy required. Next term, of course, is I need to think about what is activation energy. And that is the energy that is used to kickstart a reaction. Fancy science term for kickstart is to catalyze. Why on earth would we need to speed up chemical reactions in our body? Lunch is soon. Or maybe you already had it. Don't know. Digestion is an entire chemical reaction. In fact, it's a catabolic reaction in which I'm breaking down these giant food molecules to create energy for my body. And if I didn't have an enzyme, I would not be able to digest my food that quickly. I've got enzymes in my saliva, in my stomach, along my intestines, helping me speed up that reaction. Enzymes are actually able to speed up reactions by millions, if not billions of times as fast. So we need enzymes in order to live. Let's make a couple of extra notes here. First of all, that enzymes can be reused for tens of thousands of chemical reactions in our body. And then secondly, that enzymes speed up chemical reaction rates by hundreds, if millions, if not billions of times. Another cool thing about enzymes is their names are very specific to the substrates that they work on. So for example, we could have things like lipase, which works on lipids. We could have sucrase, which works on sucrose or sugar. I could have things like protease, which works on proteins. And you might be realizing that all enzymes also end in ACE, A-S-E. How does it actually work? How does it lower the activation energy? Remember the protein glob of amino acids all bound together? I'm going to represent it using this. This glob here is my enzyme. Say that I want to catalyze a reaction where I have a larger monomer and I want to break it down into two smaller polymers. Something that looks a little bit like this. What an enzyme is going to do is it has a very specific site. And this is called his active site. The molecule that I have at the beginning, my reactant, is also going to be called my substrate. And then the molecules I have at the end are going to be called my products. What the enzyme does is in his active site, he has amino acids that are very attracted to the substrate, and the substrate will actually bind into the active site of the enzyme. The enzyme will work a little bit on the substrate, kind of moving it around, and eventually he will break it apart into the products that we desire. The enzyme really does, and how he lowers the activation energy, is by creating this ideal environment in his active site that makes the molecules actually want to react, actually want to break down or come together. Capture this in notes. So maybe my enzyme is going to be like a Pac-Man. Okay, remember that the special lining of your enzyme is your active site. Then what happens is the substrate binds to the enzyme. And the enzyme is providing this perfect chemical environment for the substrate to actually be acted upon, so that eventually I can produce my products. Maybe this is a catabolic reaction where I'm splitting my products in half. To write some steps for that, I would be like step 1, step 2, step 3. I might say that step 1 the substrate binds to the active site. Two, the enzyme provides an ideal chemical environment for the reaction to occur in. And finally, 3, the reaction occurs and your substrate is transformed into a product. Let's just capture a couple more terms here. So the substrate is the molecules at the start of the reaction. Also known as the reactants that enzymes bind. And the active site is going to be a specific spot on the enzyme where the substrate binds. This fit between a substrate and its active site is sometimes referred to as the lock and key model. Because just like a lock and a key, if the lock was the active site and the key was the substrate, only certain substrates can actually fit the active site because the active site is so specific to the substrate. Now we know a little bit about how enzymes actually work. Let's think about how to keep them from working. Why? Because as engineering students, we need to know how the thing could potentially break down so that we can prevent it. First way you can stop an enzyme from working is using something called an inhibitor. And we've got 2 types of inhibitors, competitive and non-competitive. In a competitive inhibitor is able to bind into the active site, which would then prevent your substrate from binding and the enzyme from working on it. It's called competitive because it's competing with the substrate, kind of racing to see who can get there first in order to inhibit the enzyme. So on page 10, let's get some notes for competitive inhibitors. Competitive inhibitors are molecules, usually a molecule, that binds to the active site. This is going to prevent the substrate from binding. And the enzyme from working. Talk about a second type of inhibitor, a non-competitive inhibitor. This sneaky little guy is going to bind to some place on the enzyme other than the active site, causing the enzyme to change shape at the active site. And if it changes shape at the active site enough, your substrate is no longer able to bind neatly, and the enzyme cannot act on the substrate. A non-competitive inhibitor, also a molecule, except this molecule is going to bind to a secondary site, not the active site. And what this does is it's going to cause a change in the enzyme's active site and of course this is going to prevent the substrate from binding. If you would like to include some little drawings here, get your little Pac-Man on, feel free to do that. Now we know that in order for an enzyme to work, its active site has to be very, very specifically molded to fit that substrate. And if you change the active site just a little bit, like a lock and a key, it's not going to work anymore. So the last thing we're going to discuss today is a way to change the enzyme shape entirely. Remember that enzymes are a clump of amino acids all nicely folded together. But what we could do is maybe destroy the chemical bonds between these amino acids and cause the whole thing to unravel. And of course, if your enzyme looks like this, you don't really have an active site for your substrate to bind to. It's not going to work. That process of losing an enzyme shapes because its chemical bonds are coming undone is something I'm going to call denaturation. Remember, D is a very negative suffix, so like no. And then nature would kind of be like your state of being. So what's happening in denaturation is you're having this beautiful enzyme formed out of a clump of amino acids all nicely bound together, and then it is losing its state of being. It's becoming unraveled and just kind of becoming a polypeptide. And when it loses that clump shape, I lose my active site shape. Substrate can't bind. If we give ourselves a written definition, we might say it's when an enzyme loses shape due to a breaking of chemical bonds. And this is caused by two main things. One would be extreme pH, and the other would be extremely high temperature. Now, pH is a scale that chemists use to measure the amount of hydrogen ions inside a substance. But what they're really doing is trying to figure out if a substance is neutral or is like chemically toxic. Chemically neutral substance, of course, would be water. That would be right in the middle of your pH scale at pH 7. If you start going lower, you're going to get things that are very sour and very acidic. Low pH is acidic, so things like vinegar, lemon juice, coffee, all of those are very acidic. And if you start going higher on your pH scale, you'll get things like baking soda, ammonia, borax. All of those things you can realize are starting to get a little bit more toxic. So of course, enzymes are like people. You probably wouldn't want to hang out in vinegar or an acidic thing for very long. You also probably wouldn't want to hang out in ammonia or baking soda or something really basic for very long. So what happens is if an enzyme is in an extreme pH, either something very acidic or something very basic, often the enzyme's chemical bonds will completely fall apart and the enzyme is going to lose its shape and denature. To summarize, so low pH is going to be something that's acidic, often sour. Okay. Then we'll have neutral pH, which is often pH of 7. Okay. And then we'll have high pH, which is something considered basic. pHs, either too low or too high, are going to result in denaturation. The same thing goes for temperature. If the temperature gets too hot for an enzyme, I love my pig lighter that starts fire, except he's out of fuel. If it gets too hot, the bonds will start to become unstable and they will fall apart and the enzyme will also denature. Too cold on the other hand? Well, enzymes don't have clothes. Unfortunately, what they do is they just slow down. Like all particles slow down when they lose thermal energy. And since they're slowing down, it's harder for the substrate and the enzyme to come into contact, and overall, enzymes lose their efficiency. High temperatures are going to result in denaturation as well. Then low temperatures are going to result in slower movement. This is due to less enzyme-substrate interactions since the particles are moving slower. That's it for me in enzymes. I hope you caught up on your notes. Remember from the very beginning, our jar, our chemical reaction where this was the substrate, we're trying to break it into two products. Without the enzyme, lots of energy, really slow reaction, took a long time. With the enzyme is going to bind very specifically to the substrate, right? There's a nice specific fit between the substrate and the enzyme. And he's going to make the activation energy a lot lower. And the reaction rate will be a lot quicker. And then finally, this enzyme has not changed. I can use it over and over and over again for many different reactions. So enzymes are awesome tools because we can use them all the time. They speed up chemical reactions in our body by millions of times, and we need that in order to help us with metabolism, digestion, and other chemical reactions. Enzymes are awesome. We're going to explore them in a lab and when I see you guys next. So please make sure that number 1, you complete the enzyme practice questions by midnight tonight. Number 2, you finish the enzyme exit ticket at the end of the enzyme learning pathway. And number 3, you get your lab space and materials ready for lab next class. See you then, guys. Bye. Pig lighter.